Dr. Thomas Coolbaugh will be speaking about this topic. He is an oil spill response advisor for ExxonMobil Corporation's Safety, Security, Health, and Environment Support Organization. He's also vice chair of IPCA's Oil Spill Working Group, a member of the API Spills Advisory Group, the Marine Preservation Association Dispersant Advisory Committee, and the Science Advisory Panel of the University of New Hampshire, NOAA's Coastal Response Research Center. His focus is often on the subject of the science and regulatory aspects of the use of dispersants during an oil spill. So, Tom, thank you.
Oh, great, okay. Thank you, it's a pleasure to be here. I tend to talk about this on a fairly regular basis over the last 7 years or so. So we're going to talk now just about subsea dispersant injection. So you've heard a bunch of things about mechanical recovery, certainly about the in-situ burn, surface use of dispersants. We're going to talk really about a very special case. So we'll touch through what is subsea dispersant injection, what we call SSDI. We love abbreviations, and it just gets tiresome to keep on writing out things again and again and again. We'll talk about sort of that initial proof of performance. It's something that has been talked about for a while, but really was only used to the extent that we've seen in a Macondo response. We'll talk about a safety benefit that's associated with it as well, and I'll talk a little bit about the research that's been looked at over the last, it's hard to believe, almost 8 years now. It's just incredible that that time has gone by. You already saw this and you heard the phrase encounter rate, because that's really what it's about. Most spills are small, most are close to shore, most are amenable to mechanical recovery. In the 1 or 2 times in modern history where something happens that's beyond that scope, and you start dealing with this kind of scale, we need to have a tool that we can do something with. As Paul pointed out, if you look at that vessel going through, if that's something that's doing 3 or 4 knots or even more, imagine a mechanical recovery system with a skimmer and boom trying to do that at 3/4 of a knot, where something might have been releasing that much oil every day for 85 days, and the scale of the problem is very large. So we need to think about the tool that might be right for that kind of situation. Again, the best spill is the one that doesn't happen. Next best thing is if we can pick it back up and put it in a container. But the reality for mechanical recovery, especially far offshore in an open ocean setting, is you're lucky if you get 5%. So we want to deal with something that gives us a much better opportunity to do something. So it's really about what the spill response tools are. So from my perspective, and again, I'm coming from ExxonMobil. I've been with ExxonMobil for 30 years. I've been doing oil spill response for 11 years. I'm a chemist by training. For me, it's really, let's look at what the tools are and make sure that we have available the ones that make the most sense. There's a lot of perception about dispersants. Paul went through a lot of that sometimes is misunderstood. And in reality, I don't want something taken off the decision-making process just because we might misunderstand it or be afraid of it. Again, ExxonMobil, but I'm really talking from my perspective. I do have a disclaimer that I should have put up there, but I didn't. Mine's probably just as long as anybody else's if you fill a whole page. So this is me talking. So monitor and evaluate, which sometimes people call the do-nothing option, is really not that, because we monitor and evaluate every single time. As Paul said, sometimes that is the only thing we'll do, because from a trade-off benefit analysis, sometimes going in to physically try to do something like in sensitive marshes, we might actually do more damage than good. So it might be better to let nature actually do something. During what I call the Prince William Sound incident that happened in 1989, there were cases where beaches were washed, and they were washed with warm water, not hot water, not boiling water, but because it was such a cold air temperature, you saw the steam and everything. It would have been better off in some of those cases if it was left alone, because there was enough energy where nature actually did take care of it. Industry made it look pretty, but at the same time sort of sterilized it, so it took a while for some of those to come back. So monitor and evaluate is certainly something we want to do all the time. Again, mechanical recovery, if we could do it, and most times that is what we do, that is the best option. In-situ burning, again, it was used 411 times during Macondo. It burned about 11 million gallons, which was pretty equivalent to the Exxon Valdez. And then dispersants is really what we're talking about. Surface, Paul talked about that. It can be delivered either by air or by vessel. So what we're going to talk now is Subsea, which was relatively unique, certainly on the scale that it was used during Macondo. And you may hear us use Macondo, Deepwater Horizon, Mississippi Canyon 252. Mississippi Canyon 252 was the actual block that was leased. The Deepwater Horizon was the rig that blew up and sank on April 20th, 2010 and killed 11 people. But the well that we're talking about is the Macondo well. So that's what we really call it most of the time. It's the Macondo release. The goal is really to design that strategy that does the best response. We used to use net environmental benefit analysis, which we abbreviated as NEBA. People didn't like the word benefit because there is no benefit to an oil spill, but really what we're trying to do is take something negative and make it less negative. So move in a positive direction. But we've changed the phraseology to spill impact mitigation assessment just to take it a little bit further. It's not just the environment, it's the whole ecosystem that we're trying to make sure that we optimize what that response might be, looking at the potential trade-offs in the response tools that we have. Essentially the same diagram that Paul showed, but this one's for Subsea. It's the same process. The bacteria that can degrade oil exist everywhere we've looked. Deep sea is no special case to that. They're there as well. So at 15, well, let's say 1,200 meters below the surface where the oil was coming up from the Macondo well, bacteria were found, dispersed droplets were found, oxygen consumption was observed. So it all pointed to the fact that microbial biodegradation, even at deep sea depths, works fairly well. So the challenge we have is how to create small droplets in a very deep subsea environment to prevent them from rising to the surface too quickly. The rise time for the 1,500 meters for the Macondo release was about 5 to 7 hours for the droplets undispersed to rise to the surface. The goal was to make small enough droplets that slowed down enough. And as Paul pointed out, if the droplets get small enough, even though they still want to rise, there's enough energy in the water column that just keeps them pretty much permanently entrained, where they get colonized and then degraded over a days to weeks to months time period. There were some studies that were done that showed that the half-life based on degradation and dilution was about 4.5 days for the Macondo oil. So it was diluting that quickly and actually degrading. And if in the open environment, if you were to go and look now, you wouldn't find any Macondo oil. The place where it happens to be found is in those places where they've been turned into tar balls, tar mats, where they just don't have the availability to the microbial community plus the oxygen, because it's an aerobic degradation that really is the most effective that we're really talking about here. So we'll talk about some of the observations, we'll talk about some benefits, and then we'll end up with just some long-term considerations. Encounter rate is everything. So if you think of that 1/10 of a millimeter slick that Paul was talking about, you might be looking at a slick in a scale of a release like Macondo that could be 50 square kilometers. And that's where if you think of a boat trying to go through and skim it, or a boat going through and trying to spray dispersants, that becomes a challenge. If you use a C-130 or a 727, you can do that 50 square kilometer pretty much in what we call an operational period of 8 to 10 to 12 hours, reasonably consistently. The 727 certainly gives us a lot more operational window. So we talk about the time window of opportunity, but can you get the equipment out there too? For Macondo, we were talking about something about 50 miles offshore, and if you've been in a small boat that's doing, I don't know, 18, 20 knots, it takes you a while to get out there. You do your thing, and then you have to go back again. And there were some days where the sea state was heavy enough that you couldn't go out there safely. We have something that we call in the industry, we abbreviate it as PAIR. So it's people, environment, assets, and then reputation. We value people first. We'll never put somebody out in harm's way if we can avoid it. And then we'll worry about the environment, and then as a responsible party, we sort of worry about our reputation last. Because we have the president of our shipping company called Sea River Maritime once said something about we were going to recommend the use of the dispersants in an exercise. And somebody said, how can you possibly do that? People are going to hate that you're going to bring up that horrible material. And his comment was, it's an oil spill. They already hate us anyway. So we're going to do the right thing that we know is the scientifically and technically right thing to do. So sometimes having that ability to get 5,000 feet down, 1,500 meters, all of that oil is coming out of a hole maybe 20 inches across. And if you can get there, and I assume I do have one, if you can get something down there to deliver dispersant right there, the potential for treating all of it, even before it gets to the surface, spreads out to 50 square kilometers, is pretty significant. So the opportunity to get to the freshest oil possible with the highest encounter rate possible gives you an opportunity with subsea dispersant injection that you may not have any other way. There's a fair amount of turbulence that occurs in that first meter or two coming off the sea floor, so you get pretty good mixing. This picture on the upper right, or on the right-hand side, is sometimes shown as an example of why subsea dispersant injection is a failure, because it will be pointed out, it's not in the oil plume. You know, it's like, how can you say that that's going to do anything if the dispersant, which is that white cloud, isn't even the oil? But that's actually a snapshot from a video. And if you actually watch the video, that dispersant cloud is being sucked right into the oil because you've got a jet of material coming up through the water column, and through the Bernoulli principle, there's a lower pressure area, and it actually sucks the dispersant in. So whether you had a wand that just looks like a T, or you had a ring went around it, or you had a shower head or whatever, they're all pretty effective at delivering dispersant even 1,500 meters below the surface. It's just through a coiled tube that's being pumped from the sea surface. You can do it 24 hours a day. We've developed systems now, we've been working with OSRL and others to have deep sea dispersant systems that actually sit on the seafloor that could potentially sit there even when a hurricane goes by. So it's the kind of thing that you can do even if you can't put people out there because it's unsafe. So just an example of what the system looks like. This is just a diagram of what the picture on the left-hand side is what it looked like during Macondo with the riser tube and everything else. There was all sorts of stuff there when it first happened. Ultimately, the tubing itself was cut off and you had just the hole itself that the oil was coming out of. And ultimately, that's what got capped off. But we've been doing work since then just trying to see how we can potentially deliver dispersant as effectively as possible. Paul mentioned that the dispersant to oil ratio. So if you have 20 gallons of oil on a surface application, you would add 1 gallon of dispersant. So that's that 1 to 20. For subsea injection, with some of the work that we've been doing over the last 5 or 6 years, it could be 1 to 50, it could be 1 to 100. In some cases, we see effective dispersion even at 1 to 250. So the possibility of using a lot less dispersant to do the same thing has some potentially environmentally positive benefits associated with that. This is just an example now of what was seen during dispersant use initially during the Macondo response. So it happened on April 20th, 2010. This is May 9th, 2010, when the US EPA wanted to see a demonstration of what dispersant application in Subsea could or couldn't do before they gave BP more or less the approval to continue doing it. So this is before a test. There's a rig with the yellow ring around it. That's actually one of the relief well rigs where it's drilling. So that's just a reference point, you'll see that. So with no dispersant being added, this is the expression of the surface slick. Again, coming up through that 1,500 meters, took 5 to 7 hours for that oil to get there. And then on the morning of May 10th, they started the subsea injection. And after 3 hours of that injection, there's that same rig, and you can start to see a reduction in the amount of oil surface expression. After 11 hours, that's the same rig. And the wind has shifted a bit, but the magnitude of the wind is the same, so it's not that it's just being blown away. It really does appear that there's less oil coming. In fact, the person who took these pictures said he thought that the rig or the well had been capped that day because he looked around and it looked like 90% reduction of the oil coming to the surface. They stopped the injection, and after 5 hours, the slick started to reappear. 28 hours, it started to look back like it had been before. So based on that, the US EPA agreed that it looked like subsurface dispersant injection actually has a positive effect on that oil reaching the surface. And based on that, BP was given the approval to continue using dispersants. There are other limitations that came along days and weeks afterwards, but the technique had more or less been proven out. The other potential benefit that comes along with that, if you've ever smelled crude oil, it has a real odor associated with it, especially if it has a high sulfur content. Macondo oil was not necessarily high in sulfur, but it had a crude oil smell to it. If you were a responder out there in the middle of the Gulf of Mexico, especially going into the summer, and you're wearing Tyvek suits and with potentially a respirator if the volatile organic concentrations got high enough, if you had to wear a full face respirator, it's not a very comfortable way to work. So during the dispersant use, with that less surface expression of oil, the amount of VOCs at the water surface actually decreased quite a bit. So rather than having to clear people out of the area or put people into respirators, it was actually a much safer environment. So there's a potential health benefit, especially during those initial days, because I think once you get the people out there, you have to clear stuff out, you have to get equipment in place, you have to start doing things. That's when you really need to have the possibility of those responders to work safely. So this is just an example. There were some vessels out on the water at the time, and that's what these are here. Enterprise, the Q4000, and then the green line was just dispersant application. So if you look at the chart itself, while dispersant is being pumped, and that's the scale on the right-hand side, the VOCs on the left-hand side were relatively low. And for one reason or another, on January 1st and 2nd, dispersant use was decreased. And in these cases, the VOC concentration started to go up. So it looked like there was a cause and effect. These results were not measured specifically for that, so it's just sort of an accident, a coincidence that we actually happen to see this data. There's some other data that exists that one of my colleagues at ExxonMobil took all the data he could find and then averaged them, because again, these are point sources that weren't necessarily optimal locations where you do air monitoring. But if you did an average of what those spots saw during those days over a several-week period from May to June of 2010, the main thing is there's a couple of examples here on the left in the red where it says decreased SSDI. You can see it dipped down to 0. And the next day or so, there's a spike in the increased VOC concentration. And there are some other dips and increases along with that. Again, it's not perfect data, but the indicator is that there is a potential health benefit, especially during those early stages of subsea dispersant injection during an initial response. The main thing about subsea dispersant is it's just a tool. There's a perception globally now that that is the only tool industry would ever recommend for any oil spill response anywhere. In reality, it's a special case. Again, as highlighted, over the last 10, 20, 30 years, how many times has this been done? Very few. On this scale, never before this. So this is 1.8 billion gallons of dispersant that were treated totally. 700,000 gallons of that was subsea injection. So that's a large number. Still relatively small when you consider it as 200 million gallons, roughly 150 to 200 million of oil that was released. So it's a relatively small percentage. It's still a lot, there's no doubt about that. But it was a single case, again now almost 8 years ago. We haven't seen that since. Dispersants are used around the world for much smaller situations. But if you happen to have another situation like a Macondo, there may be several reasons why you might want to consider having it on the table, and that's really what we're talking about. We want to make sure it stays there. So we've done work just trying to understand how we measure effectiveness. If you imagine a surface application, you have a floating slick, you spray some dispersant, you agitate it, you look at how much oil is left on the surface. So you can get a 0 to 100% fairly clearly. You can tell if it worked. From this case, how do we know? Other than it taking that much longer to rise to the surface, we're not necessarily measuring what comes up. Because whatever does come up might be spread out much further, it might be farther down current, you might not know exactly where it's coming. So we did some work with, through IPICA, the API, and International Association of Oil and Gas Producers, to do some work at SINTEF, which is a Norwegian research organization, and CEDRA, which is a French research organization, to try to come up with a bench scale test of measuring dispersant effectiveness for subsea injection. And what we're really trying to understand is droplet size. As Paul mentioned, if the oil is floating on the surface, it's a black slick. If you disperse it, you get these very small droplets that are about the width of a human hair, and it starts to look very light brown. In fact, we could say it looks like cafe au lait. It's got sort of that color to it. But it's droplet size related. So we want to come up with some way to measure droplet size distribution. So CEDRA and SINTEF came up with their own approaches. And I call these bench scale. One of them is this tall, and the other is maybe this tall. So it's not really bench scale, but it's much smaller than going out in the open ocean. Or in the case of SINTEF, they have a 6-meter tank. This is quite a bit smaller. So they made a plume. This is undispersed. In the case of SINTEF, you can add dispersant to it, and then you can measure the droplets that come out of that. CEDRA did the same thing. It's kind of interesting. They injected it from the top and watched it go down, which they, well, that's kind of silly. Not really, because again, it's not really all that buoyant at that point. It still wants to float, but the droplets are so small, they stay pretty well dispersed into that long enough to be able to measure what's going on. So based on both of those, we looked at 4 different crudes, 3 different dispersants, different setups, clearly, but then different energy regimes, and the end result was that the left-hand side is the French CEDRA result, the right hand is the Norwegian SINTEF. If you look at droplet size decreasing from left to right in both of those, again, smaller droplets is good, increase going to the right. Small is good on the left. Effectiveness, high. So in case of CEDRA, what they looked at is effectiveness versus droplet size. Most of what they looked at in just this chart, they're up in the good quadrant. down on the bottom right, these red data points, was a particular crude oil that didn't disperse very well. And it just clearly separates out. And that's what you want for a bench scale test. In the case of the Syntef approach, they just measured droplet size distribution, and again, smaller is better. So as you shift to the left on these right-hand charts, smaller is better. So it goes green, blue, red in their small tank. They had that large tank, and it goes green, blue, red. So again, they saw the same thing for the same dispersant. So it actually gave good reproducible results that allows us then to at least rank dispersants. So from that standpoint, that's what a bench scale should be. This is something that we did, you saw earlier, that OMSET test tank up in New Jersey. This is one from it. We had a rig set up that could release oil into it. It's about 10 or 12 feet deep. Without dispersant, you just see this black ring that comes to the surface and spreads. As soon as you add dispersant to it, you get this brown cloud that stays below the surface and never actually rises to the surface to form a slick. And that's all in a matter of a fraction of a second. Doesn't even happen in 10 feet. It disperses that quickly. And as Paul said, we're not sinking it. It still wants to float, and eventually, if you left it alone, it would. But it disperses very readily. And at this point, it's moving, this bottom right-hand figure, it's moving with a small surface current that's in the tank. The upper black stuff, meanwhile, moved down the tank with the wind. So it gives you much different control of where it's going to go. And if you happen to be in an environment where you have an onshore wind with a slick, it's going to push it onshore. As soon as you put it into the water column, it goes with the water currents themselves, which generally go parallel to the shore, so you're actually not pushing it onto the shoreline. So you can control what might ultimately happen. There are lots of references out there. IPICA did some work, API did some work. Gulf of Mexico Research Initiative has been doing a lot of work over the last 6 or 7 years, and VJ John, professor, will talk about that in just a second. I encourage people to go out and look at this data, though, because there's an awful lot of it, and it's really about having the right choice in the event of a bad situation, because an oil spill is a bad thing. But we want to have the full suite of tools available to us. We're looking, oops, let me go back here just for a second. The stuff that's being looked at now is really what are those long-term fate and effects for dispersant use, especially in the Gulf of Mexico with that kind of volume and those kind of concentrations over a 3-month period. Again, that's a unique situation. We're pretty good about solving the last problem. So I have no idea what the next spill might be, but I don't think it'll look like something we've seen before, at least at that kind of scale. So I just want to end it with use the appropriate response tools. So use that NEBA, SEMA type decision-making process. Talk early. Certainly talk to stakeholders before something happens, because the last thing you want to do is have this discussion on the day of the spill. That's not a happy time. Highest priority is always human health. So whatever we can do to at least preserve that and certainly not make it worse. And then understanding what the potential benefits are. So subsea dispersant does give that possibility of getting out there quickly, treating something very effectively, and for whatever time period that might need to be. But certainly there are things we can do to optimize it. VOC reduction certainly has some safety components, but then it's really what are those long-term fate effects in that subsea environment that we need to consider. And I think that's it. Thank you very much.